Okay. I'm sorry?
It's okay. We don't need a book.
Pinky, if you're going to do a job, do the job. Like you're getting paid big money for this.
That felt threatening. It's like holding the heavy.
Okay. So, chapter 8 deals with logarithms, and we're going to see the connection between logarithms and exponential functions today. I have talked a little bit about logarithms, and I've told you that one of the applications of logarithms that allows you to solve any exponential equation. So back in chapter 7, we saw that we could solve certain exponential equations by making the bases the same. Once the bases were the same, and you had both sides expressed as a single exponential expression with the same base, we said then the exponents were equal, and we solved them that way. Then we saw that if you couldn't make the bases the same, you could use your graphing calculator to solve them, but that only gave you an answer that you approximated the answer because in many cases it was an irrational answer. So now we'll see how we can use logarithms to solve those types of equations, and then we'll be able to state the solution or solutions as an exact value. So that's one of the uses of logarithms. So as it says there, they were developed over 400 years ago, but still have numerous applications in the modern world. Again, they allow us to solve any exponential equations. But logarithmic scales use manageable numbers to represent quantities in science that vary over vast ranges, such as energy of an earthquake or the pH of a solution. Logarithmic spirals model the spiral arms of a galaxy, the curve of animal horns, the shape of a snail, the growth of certain plants, the arms of a hurricane, and the approach of a hawk to its prey. So, some key terms. Obviously, we'll talk about logarithmic functions. We'll also talk about common logs, and then we'll get looking at logarithmic equations. So in this chapter or this section, we'll demonstrate that a logarithm is actually the inverse of an exponential function. Right? So that's where the connection is. The inverse of an exponential function is a logarithmic function, and the inverse of a logarithmic function is the inverse of an exponential. Remember, when we graph the inverse of a function, we said that they were reflections about the line y equals x, but that's not really what we use to graph an inverse. What we did is we took points on the original graph and we switched the x and y values around. And that gave us the points on the inverse. That's how we graphed an inverse. The result is the reflection over the line y equals x, but that's not normally the easiest way to do the graph of an inverse, right? Also remember that when you have an equation and you want to write the equation of the inverse, our first step was to switch x and y around, and then we solve for y. So we did those things already in this course, right? Back in Unit 1, we did all that stuff. It was part of our transformations. So we're going to sketch the graph of y equals log base c of x. So logs will have a base. It's a subscript. See how that c is written down quite small, low? That's a subscript. So logs have a base. So we're going to talk about that. And there's going to be restrictions on the base. It has to be greater than 0, and it also can't equal 1. So we're going to see why that's true. We'll look at the characteristics of the graph of y equals log base c of x. We'll explain relationships between logarithms and exponents. We'll express logarithmic functions as exponential functions and vice versa. And then we'll evaluate logarithms using a variety of methods. So, to investigate a logarithm, it says use a calculator to determine the decimal approximation of the exponent x in each equation to one decimal place. All right? So first, if you have 10 to the power x as your base function, that's an exponential function, obviously, right? When x equals -1, that'll be 10 to the -1, or 1 over 10 to the +1. Remember, to evaluate powers, we need positive exponents. So if x equals -1, y will equal 10 to the -1, which is 1 over 10 to the +1, or 1/10, which is 0.1. When x is 0, so we'll go back and do the y values that were given and find out what the corresponding x value is, but let's deal with the places where we're given the x value. When x is 0, y would equal 10 to the 0, which is 1. When x equals 1, y will equal 10 to the 1, which is 10. So we can fill in those three y values given the original x values, and again, we're using the equation y equals 10 to the power x. Right? That's coming from this right there. Then, if you're given the y value and you want to know what the x value is, we're saying 10 to what power is 0.5. We can do that graphically. So we can go to our graphing calculator, and we can graph y equals 10 to the power x as y1, and y2 will be 0.5. And we want to know where these two graphs intersect. That'll be the x value that makes this equation true. Zoom 6 sets our windows to their standard settings. And because that second line is just y equals a half, that's why that line is so close to the x-axis. So we want to find the point of intersection. Second function trace, number 5 for intersect. Enter, enter, enter. You can see that the x value is negative 0. Looks like negative 0.3, and it is. That's the x value though, right? Not the y value. We're given the y value. Negative 0.3 rounded to the nearest tenth. The next two we have to find is what value of x will make 10 to the power x equal positive 4. So we'll change that second equation to positive 4. We'll graph it and find that point of intersection. That's 0.6. And where does 10 to the power x equal positive 8? Whoops. Our x value is 0.9. On the next page, there is a grid. So we're going to graph this now. We're going to graph the line y equals 10 to the power x using this table of values that we have completed. So on the next page, let's put our xy axes on there. We're going to have more positive values of x. I'll put my x-axis kind of in the middle, but my y-axis, I'm just putting it a little bit over to the left here of middle. Right? And if you refer back to the table of values, you got the point -1, 1/10. And we looked at the graph of exponential functions back in the last chapter, so this part here isn't anything new. We've got the point -0.3, 0.5. We've got the point 0, 1. We saw that for our base exponential functions, the y-intercept was always 1. This when x is 0. 0.6 comma 4, approximately right there. And then 0.9 comma 8. Approximately right there. And then we have 1 comma 10. Approximately right there. So this is the graph of y equals 10 to the power x. That's terrible. Try that one more time. The x-axis is a horizontal asymptote. Looks something like that. We talk about the characteristics on the previous page. We can fill that in. The domain was all real numbers. It went from negative infinity to positive infinity. There are no restrictions on x. Our range, though, goes from 0, which is not included, up to positive infinity, which is also not included. So therefore, we use the rounded brackets. There is no x-intercept because the x-axis is an asymptote. The y-intercept is the point 0, comma 1. And we have an asymptote, which again is the x-axis, the line y equals 0. So we saw all this before when we looked at the graph of exponential functions. As the base changes, all it changes is how large the values of y get, how quickly they get larger or smaller. We saw before that when the base is greater than 1, we get an increasing function. What we have here, between 0 and 1, we get a decreasing function. But whenever the function is increasing, changing the base, as the base increases, the values of y just get larger faster. That's all that happens. Okay? Now, 3 says copy and complete the table of values for y equals 10 to the, or excuse me, x equals 10 to the y, which is the inverse of y equals 10 to the x, right? We started with y equals 10 to the x. To get the inverse of that, normally our first step is to change x and y. And then normally we get y by itself. But based on what we've learned right now, we cannot do anything to get y by itself in that equation. But we have the table of values from y equals 10 to the x. Remember, to get the table for the inverse, you just take the table from the original and you switch the x and y values around. So if you refer back to what we did on that first page, the first point we have was negative 1 comma 1/10. The point on the inverse will be 1/10 comma negative 1. You switch the x and y values around. The next point we had in that table was the point negative 0.3 comma 0.5. That was the point on the original graph or the original table. Well, the point on the inverse would be 0.5 comma negative 0.3. The next point on the original table was the y-intercept, the point 0 comma 1. The corresponding point on the inverse would be 1 comma 0. Again, switch the x and y values around. The next point on that table was 0.6 comma 4. So the point on the inverse will be 4 comma 0.6. The next point on that original table was 0.9 comma 8. So the point on the inverse would be 8 comma 0.9. And the last point on the table was the point 1 comma 10. So on the inverse, the point is 10 comma 1. So now we can take these points and graph them on the graph on the previous page. So we can graph the inverse as well. So again, the first point I have in my new table is 1/10, comma, -1, which is there approximately. 1/2, comma, -0.3, approximately there. 1, comma, 0. 4, comma, 0.6. 8, comma, 0.9. And 10, comma, 1. In this case, the y-axis will be an asymptote. It'll be a vertical asymptote. So it's going to look something like that. Now remember, we just graphed the inverse of the exponential function, and we stated on the first page that the inverse of an exponential function is a logarithm. So we've just graphed a logarithmic function. We stated at the very first today that a logarithm is the inverse of an exponential function. So we started with an exponential function, and then we generated the points for the inverse by taking them and switching the x and y values around from the original table of values. So we graphed the inverse of that exponential function, and we've said that a logarithm is the inverse of an exponential function. So we've just graphed a logarithmic function. Okay? It is an inverse of an exponential function, or they are reflections about the line y equals x. Now, if we state the characteristics of this one has a domain which would be from 0 to positive infinity, because the y-axis is a vertical asymptote. The graph is to the right of that. The further down it goes, the closer it'll get to the y-axis, but it'll never actually touch it. Okay? The range would be all real numbers. It goes up and down forever. So from negative infinity to positive infinity. This graph has an x-intercept. That is the point 1, comma 0. But there is no y-intercept. And again, our asymptote is the y-axis, which is the line x equals 0. Okay? Remember that when you look at a function and its inverse, you switch the x and y values around, and that meant that the domains and ranges were also switched around, which is what happened here. Now, number 4 says, use the log function on a calculator to find the decimal approximation for each expression. The first one is the log of 0.5. So your log key is down here on the left, just to the left of the number 7 key. And if you take the log of 0.5, you get negative 0.3, which matches this point right there. When x is 0.5 and you take the log of it, you're going to get negative 0.3. The next one it says to take is the log of 4. If you take the log of 4, you get 0.6, which is this point right there. When x is 4 and you take the log of 4, you get 0.6. And the last one it says is the log of 8, which you should guess is going to be 0.9, and it is, because that's that point right there. So really what we've done here is we have the table of values for y equals log x. Right? We let x equal 0.5, and when we put that in for the log of 0.5, we got negative 0.3. When we let x equal 4 and we took the log of 4, we got 0.6. That gave us the y value. And same thing with the 0.8, comma 0.9. So this table matches the equation y equals log x, and so this graph matches the graph of y equals log x. This one was y equals 10 to the power x. That was the exponential function we started with. Then the inverse is y equals the log of x. Now remember, we said that all logs have a base. And when you take the log of any number using this key, that is known as a common log, and that means it's base 10. So this means that this is actually y equals log base 10 of x. But when no base is written, that means it's a common log. That means it's base 10. We are going to start looking eventually here at logs when the base isn't 10, and we'll see how we handle those. Because whenever you use the log key on your calculator, that means you're taking the common log of whatever it is you're putting in after you type in log. It means it's base 10. So again, we will see how you handle logs when the bases are not base 10. But when you just hit that log key, that means you're taking a common log, which is base 10. So again, this is the graph of log x, or log base 10 of x. Okay, so for the exponential function y equals c to the x, the inverse is x equals c to the y. Remember, that's what we said. This was x equals 10 to the power y. But we can also write that as y equals log base 10 of x. These two equations are the same. They're just in different forms. The first one is exponential form. The second is logarithmic form. They are the same equation. They are just in different forms. So this means then that we can convert. We can convert from an exponential function and write it as an equivalent logarithmic function. And we can start with a logarithmic function and we can write it as an equivalent exponential function. And there's usually a question on the diploma exam, usually a multiple choice, where that's what they ask you to do. They'll give you an exponential function and you'll have to pick which of the four responses there is the correct logarithmic function for that same exponential. Or they may give you a logarithmic function and you'd have to pick which exponential function matches that logarithmic function. So you have to know how to do that. Okay, and we'll talk about how that's done. But again, on the right there, a logarithmic function is a function of the form y equals log base c of x, where c is greater than 0 and not equal to 1, and it is the inverse of y equals c to the x. So a logarithm can be written as an exponent. Okay, and a common log is a log with a base of 10. So here's how you convert from one form to the other. Okay, if you start with c to the y equals x, so that exponential function has a base of c. Notice that the logarithmic form also has a base, and it is the same. The base of the log will equal the base in the exponential form. The base in the exponential form will equal the base in the logarithmic form. So in order to convert from one to the other, here's what I always say. You start with the base and cycle through. For example, you know that 10 to the power 2 equals 100. That is true. If you want to write that in exponential form, start with the base and cycle through. Remember, the logarithmic form also has a base, and it is the same as the base of the exponential form, which is 10. So this would be log base 10. That's the first part of it. To know what order the other parts go in, start with the base and cycle through. So what I mean by that is cross over the equal sign. From the base of 10, you cycle through across the equal sign to the 100, and then from the 100 back across to the exponent of 2. This tells you what order the other pieces are written in. So after log base 10, after the base 10, the next thing you write is 100. And after the 100, you're going to have equals 2. Start with the base and cycle through. It tells you what order they're written in. So what we have here is log base 10 of 100 is 2. or just log of 100 is 2. Because remember, when no base is indicated, that means it's base 10. So you could check this on your calculator. If you take the log of 100, it does equal 2. It's true. Our first statement is true. And when we convert it to logarithmic, now we see our second statement is also true. Right? You know that, let's say 10 to the power 4 is 10,000. That is true. That's an exponential expression. Well, you can write it as a logarithmic expression by, again, starting with the base and cycling through. The base of the log will be the same as the base in exponential form. The exponential form has a base of 10, so the log will also have a base of 10. To get what order the other pieces go in, start with the base and cycle through. So after you have your log with a base of 10, after the 10 comes the 10,000. And after that, that will equal 4. There's the exponential form, there's the logarithmic form of 10 to the power 4 equals 10,000. And again, you could check this on your calculator by taking the log of 10,000. It does equal 4. So that logarithmic statement is correct. It came from a correct exponential statement, but this also shows us that the way we wrote the logarithmic is also correct. You see, if you switch the 10,000 and the 4 around and said log base 10 of 4, well, that won't equal 10,000. The log of 4 is not 10,000. It's a decimal, right? So again, this just shows us that the order that we wrote the logarithmic statement in is correct. It is true. It is correct. So we did the correct conversion, right? But you're going to see these with powers other than 10. For example, if you had 6 to the power 2, well, we know that equals 36. That is true. The correct logarithmic form of that would be log base 6 of 36 equals 2. Remember, the bases are the same. The exponential function has a base of 6. The logarithmic function will also have a base of 6. And after that, you start with the base and you cycle through. This tells you the order that the other parts are written in. After the base 6 comes the 36, and after that comes the equals 2. But you can't check this on your calculator yet because we don't know how to deal with logs with other bases. We will learn that, but we're not there yet. Right now, we're just doing the conversions. Okay? And sometimes you're going to get exponential expressions or equations where you have a variable in them. So let's say you had 2 to the x equals 30. That's an exponential equation. You can write that in logarithmic form by starting with the base and cycling through. The base of the exponential function is 2. That will be the base of the logarithmic function. So it'll be log base 2. And then again, to get what order the other pieces go in, start with the base and cycle through. After the base 2 becomes the 30, after that comes the equals x. There's the logarithmic statement that matches that exponential. These are the same equations, they're just in different forms. One's in exponential form, the other's in logarithmic form. They are the same equation, just in different forms. The same is true if you go from a logarithmic, to an exponential. Let's say you had log base 5 of 10 equals x. And you wanted to write that in exponential form. You do the same thing. You start with the base and cycle through. So this log has a base of 5. So if you write it in exponential form, it'll have a base of 5 as well. 5 to some power. To know what order they're written in, start with the base and cycle through. After the 5 comes the x. So it'll be 5 to the power x equals, after the x comes the 10. So that is the exponential equation that matches that logarithmic equation. They are the same equation. They're just in different forms. One's logarithmic, the other's exponential. Okay? If we had, let's say, log base 2 of x equals 12 as a logarithmic equation, we can write that in exponential by, again, starting with the base and cycling through. This log has a base of 2, so the exponential function will have a base of 2. To get what order the other pieces are in, start with the base and cycle through. After the 2 comes the 12, so it's going to be it's going to be 2 to the power 12, and after the 12 comes the x. So that is the exponential equivalent to log base 2 of x equals 12. If you write that as an exponential function, it will be 2 to the 12 equals x. So again, they are the same equation. They're just in different forms. Right? We haven't taken the inverse of anything. We're just switching it from one form to the other. They are the same equation. They're just in different forms. If you take the inverse, now you're going to get different equations because you're going to switch the x and y's around. And then your graphs would be reflections about the line y equals x. That's not what we're doing here. We're just changing the format of the equation. You can write every exponential function as a logarithmic function. You can write every logarithmic function as an exponential function just by simply starting with the base and cycling through and remembering that the bases are the same. So this question says or asks us to evaluate these logarithms. Now, notice that the first two and the last one, the bases are not 10. So you cannot directly use the calculator to do it. But here's what we can do. If I want to know what log base 7 of 49 is, I can say, well, what does that equal? That equals x. So let's let it equal x. And you can use any variable you want. But now to evaluate this, I'm going to change the format. I'm going to change it from logarithmic to exponential by starting with the base and cycling through. This log has a base of 7, so in exponential form, the base will be 7. To know what order the other pieces are written in, start with the base and cycle through. After the 7 comes the x, so it'll be 7 to the power x equals 49. So now what does x equal? Obviously, x equals 2, because 7 squared does equal 49. So we're beginning to see what a logarithm really means. When you have log base 7 of 49, it's really asking 7 to what power is 49? That's what it's really asking. 7 to what power is 49? So same thing with question B. If I want to know what that equals, let's let it equal x. And then we'll convert from logarithmic to exponential. The base of the log is 6. That'll be the base written in exponential form. And again, to get what order the other pieces are written in, start with the base and cycle through. It'll be 6 to the power x equals 1. So obviously x will equal 0. Right? Anything to the power 0 equals 1. Again, when you see log base 6 of 1, it's really asking you 6 to what power is 1. That's what it's asking, because that's what you get when you change it to exponential. Okay? Question C. This is a common log, no base indicated, so you can just use your calculator if you want and take the log of 0.001. It is -3. That's the value of this, -3. But here's why that is true. If we set this equal to x, and then we convert from logarithmic to exponential, remember, common log means base 10. The base of the log will be the same number for the base of the exponential, which will be the number 10. To get what order the other pieces come in, we convert by starting with the base and cycling through. It'll be 10 to the power x equals 0.001. So you can solve this exponential equation like we did back in the last chapter. 0.001 is 1 over 1,000. Right? Because there's 3 decimals, 3 digits after the decimal. That means you're dividing by 1,000. So that is 1 over 10 cubed. 1,000 is 10 cubed. And if you move that 10 to the top, you'll get 10 to the -3. That's the answer we got. -3, but that's why. Okay? We did it on our calculator, and then we did it by solving the exponential equation. So you see where that answer of -3 comes from. It's asking 10 to what power is 0.001, or 10 to what power is 1 over 1,000. Right, so for this next one, again, we want to know what this equals, so we could let it equal x, and then we would convert from logarithmic to exponential by starting with the base and cycling through. Remember that the bases are the same no matter what form you're in. So if I want to write this in exponential, it has a base of 2 because that's the base of the log. Cycling through tells you what order the other pieces go in. After the 2 will be to the power x equals, after that is our root 8. So right now we can't use our calculator to calculate this directly because that log key only deals with common logs, base 10, like question C. So we can solve this exponential equation. The root of 8 will be 8 to the half. And we can write 8 with a base of 2. 8 is 2 cubed. Would also be raised to the power a half. And now when you multiply the exponents on the right, you're going to get 2 to the 3 halves. Bases are equal, so the exponents are equal as well. X equals 3 halves is our answer, 1.5. Okay, now to check this on a calculator, you could graph, but you'd have to graph the exponential function, right? You'd have to graph the exponential function. 2 to the x equals root 8. So here's what that would look like. Y equals, we'll put in there 2 to the power x as our first equation. Our second equation will just be the root of 8. And we'd want to find the point of intersection between these two. And it should be 1.5. And it is. So you could check this on a graphing calculator, but you would first have to write the equivalent exponential function. Okay? You first have to do that. So down below, we want to evaluate these. So again, you can start by letting that equal x. So for question A, when we write that as an exponential function, it'll be 2 to the power x equals 32. Start with the base and cycle through. Remember, the bases are the same. Whether it's in logarithmic form or exponential form, the bases are the same. So the log has a base of 2. The exponential function will also have a base of 2. And this one we can solve by making the bases equal. 32 is 2 to the 5th. So x equals 5. And if you wanted to check this on your calculator, you would have to use the exponential function right now. Graph y equals 2 to the x, graph y equals 32, find the point of intersection. Okay. Question B, log base 9 of the 5th root of 81, which is 81 to the 1/5. We want to know what that equals. So let's let it equal x. If you write that in exponential form, it'll be 9 to the power x equals 81 to the power 1/5. Start with the base and cycle through. We can make both of these have the same base of 9. 81 is 9 squared. You could make them both with a base of 3. That's just extra work that you don't need to do, but it'll work. So on the right, when you multiply the exponents, it'll be 9 to the power 2/5. Bases are equal, so the exponents are equal. X equals 2/5. There's our answer. And again, if you wanted to check that, you would have to take this exponential function, graph the left and the right side, find the point of intersection. It would be at 0.4, which is what 2/5 is. Question C, well, that's a common log. So you don't need to write it as an exponential function. You can just use your calculator. That's really asking 10 to what power is 1 million? And the answer is 6. But you can do that in your calculator. you can take the log of 1,000,000. That is a common log, no base indicated, which means it's base 10. And that's what the log button on your calculator does. Right? But for D, you can't use the log key directly. This is asking 3 to what power equals 9 root 3. That's what it's asking, right? Just like number or question A is asking 2 to what power is 32. And B is asking 9 to what power equals the 5th root of 81. That's what it's asking. Question D is asking 3 to what power equals 9 root 3. We want to know what that equals, so we set it equal x, and then we convert from logarithmic to exponential. Start with the base and cycle through. So this can be solved again by making the bases the same. 9 is 3 squared, and that's multiplied by the root of 3, which is 3 to the half. On the right, we're multiplying powers with the same base, so we add the exponents and keep the base the same. That'll be 3 to the 2.5, 3.5, or 2.5, excuse me. Bases are equal, so the exponents will be equal as well. The value of that is 2.5. Now here's another way you could check this. We found our answer to be 2.5. Again, log base 3 of 9 root 3 is asking 3 to what power equals 9 root 3. That's what it's asking. If you take your calculator and you go 3 to the power 2.5, you're going to get a decimal. Well, that should equal 9 root 3. Because again, log base 3 of 9 root 3 is asking 3 to what power is 9 root 3. We said our answer x is 2.5. That is the power that 3 is raised to equal 9 root 3. So if I go 9 root 3 in my calculator, I should get the same decimal, and I do. There's another way you could check it. Right? If we go back to question A, this is really asking 2 to what power is 32. We found our answer to be 5. Well, that's correct. 2 to the 5th is 32. Question B, that is asking 9 to what power is the 5th root of 81. We found our answer to be 2/5. So 9 to the power 2/5 should equal the 5th root of 81. 9 to the power 2 over 5 is that value. That should be the same as the 5th root of 81. And it is. So there's another way you could check these. Okay. So we got a couple statements here. If C is greater than 0 and C can't equal 1, which remember those are the restrictions on the base. The first statement there says that log base C of 1 equals 0, because if you write that in exponential form by starting with the base and cycling through, you'll get C to the 0 equals 1, which we know is true. So therefore, that first statement is true as well. Basically, this tells us that the log of 1, no matter what the base is always 0, always. Because if you write it as an exponential function, whatever the base is, it'll be raised to the power 0. That will always equal 1. The log of 1, no matter what the base is always 0. The second statement says that log base C of C equals 1. Because if you write that in exponential format, you'll get, starting with the base and cycling through, C to the 1 equals C, which is true. We know that's true. So that means this first statement is true as well. So what that really means is that whenever you take a log of something, and that something is the same as the base, the answer is always 1. Log base 5 of 5 would be 1. Log base 12 of 12 would be 1. Log base 1,000,000 of 1,000,000 will be 1. Always. Okay? And then we're going to see as we go through, these other statements are going to become true as well, but we're also going to learn about rules, how we deal with them, so we don't have to remember these rules. In other words, if you have the log of a power, what do you do to that in order to work with it? So we're going to learn about that. You don't have to memorize any of these rules. they will become obvious to you as you learn more about how we deal with different logarithms. Okay, so we'll see about that. So on the previous examples, we had an expression where you had the base and you had what you were taking the log of. And we want to know what does that equal. But you're also going to see ones like this. So now we're starting to kind of look at solving some equations involving logarithms. We want to know what value of x exists such that the log base 5 of that number equals -3. And in most cases, when you're doing these, you're going to always convert from one form to the other. In this case, it's in logarithmic form, so we're going to write it in exponential form by starting with the base and cycling through. So that would look like that. Remember, the base of the log will equal the base in exponential form. The log has a base of 5, so the exponential will also have a base of 5. And to get what order the other pieces go in, start with the base and cycle through. That tells you what order the other pieces go in. After the 5 comes the power -3. Remember, the 5 is the base. So if you have a base, you got to have an exponent. That's what comes next. That's what the -3 is. And then you're going to equals whatever you get when you cross the equal sign for the last time, when you cycle over the last time. That's your x. And now you can evaluate this. That'll be 1 over 5 cubed, or 1 over 125. There's our answer. Now, you could check this on a graphing calculator by making that first equation log base 5 of x. Now, depending on your operating system, if you have an older operating system, you don't have the ability to change logs with other bases. I will show you a different way that we'll be doing that as we go through more laws of logarithms. But to see if you have it, if you go, and I'm trying to remember, I think it's alpha zoom for alpha F3. Nope, that's not right. So let me try something else. Alpha F2, there we go. So alpha F2, the window key. Alpha, the window key, and you can see number 5 in this list is log with a different base. So if you go alpha and then hit F2, if you don't see that, then that means you don't have the newer operating system. You won't be able to use this on your calculator. Again, I will show you a different way as we go through this of how we can do that. But in this case, I want to go log base 5 of x. So I use my arrow key to go from the base over to the argument. The argument is what you're taking the log of. So there's our first equation. Our second equation will just be -3. I graph them, and I find the point of intersection. Now, it looks like the logarithmic graph doesn't, it looks like it stops, but remember it doesn't. When we graphed the inverse of that exponential function, the y-axis was a vertical asymptote. This graph extends down forever, keeps getting closer to the y-axis. Calculator just doesn't show that, but it should give us the point of intersection. Now, my first curve, it goes where x is 0. The graph of the logarithmic function is not defined at x equals 0 because the y-axis is an asymptote. So I got to move over with my cursor until I get a y value displayed, and then I can finish it off. That's my second curve. So there we go. We get 0.008 as our answer, which is what 1 over 125 is. 1 divided by 125 is 0.008. So we just checked our answer. It works. Question B. Notice here the variable is the base of the log, but it doesn't matter. We can solve this by starting with the base and cycling through. The base of the log will be the base in exponential form, which is base x. Right? Cycle through tells you what order the other pieces are written in. After the x, which is a base, we're going to have the number 2, which is our exponent. And then after that, we'll have equals the last part, which is a 36. Obviously, the answer here is 6, because 6 squared does equal 36. Log base 6 of 36 is asking, 6 to what power is 36? The answer is 6. And you could check that on the graphing calculator like I showed you. Okay? Question C. If I want to know what x is, I can convert from logarithmic to exponential. I start with the base and cycle through. So I'll have 64 to the 2/3 equals x. I can evaluate this. What I would do here is I would raise both sides to the power, actually, no, that's not true. I can just evaluate this because power 2/3 means the cube root of 64 squared. A rational exponent can be written as a radical. The denominator tells you what root it is, the numerator tells you what power it is raised to. The cube root of 64 is 4, and 4 squared is 16. You can do that on your calculator, the cube root of 64, but it is 4. Yep. Number 4 in the list is cube root. Cube root of 64 is 4. Okay, so determining x, again, we start by converting from logarithmic to exponential. The first one, you'll get 4 to the negative 2 equals x. 4 to the negative 2 is 1 over 4 squared, or 1 over 16. There's the answer. And you can check that on the calculator if you can graph log base 4 of x. If not, you're going to have to wait until we learn how you can graph that without having that newer operating system, that function. Question B, to find out what x is, you convert from logarithmic to exponential. Start with the base and cycle through. The base of the log will equal the base in exponential form. So that'll be 1 over 16 to the positive 1/4, right? You cannot evaluate expressions with negative exponents. We got to make them positive. And positive 1/4 as a power means the 4th root of 16. Really, the 4th root of 16 to the power 1. But power 1 doesn't change it. The 4th root of 16 is 2. To get that on the calculator, you'll have to put the 4 in first, and then math number 5 for the x root. 4th root of 16, 2. And for C, start with the base, cycle through. Convert from logarithmic to exponential. It will be x to the 2/3 equals 9. So to solve this one, to know what x equals, we want x to the 1. We need the exponent of x to be 1. And we can do that if we raise that to the power that's the reciprocal of 2/3. That'll be power 3 over 2. The reason that works is because when you multiply the exponents together, you'll get x to the 6 over 6, which is 1. And that'll equal the square root of 9 cubed. Square root of 9 is 3. 3 cubed is 27. So there's our answer. Okay, I'm going to put some questions on here for you to practice. Page 380 to 381. Questions 2 through 4, 12, 15, and 16. You should do those for practice. I will post the solutions on Google Classroom so you can check your work. But first, you're going to write your quiz on chapter 7. So it gives you a half hour to do that. Okay, the last question is a bonus.